So our next speaker is James Thompson from JILA.
All right.
I'll give you a 5-minute warning, okay?
Sounds great. So it's great to see everyone after all the time away at COVID, to see the community together again. Hi. Thank you to the organizers. Putting this kind of thing together is an amazing amount of work, but bringing the community together is so important. So I'm very happy to be here. Thank you for the invitation. So I'm going to tell you about some work we're doing in my lab at JILA in the University of Colorado, where we're exploring entanglement-enhanced Matterwave interferometry realized inside of a high-finesse cavity. So as you heard in the previous talk, we do the same thing in my lab. We really think about creating correlations and entanglement between atoms, facilitated by putting the atoms inside of a high-finesse cavity. So a mirror here, a mirror here. The atoms interact via the light field. In the experiments I'm going to describe today, we use all of quantum mechanics. We use unitary dynamics, like we were hearing about in the previous talk, but we also use the quantum measurement process and dissipation for various experiments. We do this in 3 different systems. There are 3 different cavity systems, one based on rubidium, a standing wave, a strontium standing wave cavity, and a strontium ring cavity over here. At the moment, what we're exploring, the types of physics, include this entangled Matterwave interferometer I'm going to talk about. We're exploring dynamics in many body systems here and a continuous superradiant laser. And we're actually seeing some interesting continuous laser light emission that we think is related to sort of Carl-like physics, this collectivist atomic recoil lasing kind of mechanism, but in a truly CW way, where it just sits there and outputs light all the time. And you can hear about that from Vera on Thursday at the poster session. So in the rubidium system, we look at generating entanglement between atoms. And so let me just remind you that if I have a collection of N atoms I want to build a quantum sensor out of, at the end of the day, I need to measure sort of what's the outcome of my sensing, okay? Like what's my value? And so we can actually think of that by the collection of N atoms described by a block vector, and there's some quantum fuzziness associated with unentangled atoms that sets an angular uncertainty of 1 over root n radians in your ability to read out this quantum sensor, okay? And so if you introduce entanglement between the atoms, it really allows the atoms to conspire together to either partially cancel each other's quantum noise or to make the phase that accrues in the sensor accrue more quickly. But in either case, you get a more precise sensor by introducing entanglement between the atoms. So how well are we doing as a community on this? There are actually many, many different approaches based on ions and ion traps, based on collisions between neutral atoms, based on Rydberg interactions. And what I will highlight for this talk are the points that are sort of closed here, and those are based on light-matter interactions, either through unitary light dynamics or through things called quantum non-demolition measurements. And so what I'm plotting here on the vertical is the enhancement over the standard quantum limit. So 1 means you're at the standard quantum limit, and this is versus year. And so about the best we can do at this point is about 18 to 19 dB improvement over the standard quantum limit in rubidium. And that's in Mark Kacevich's lab at Stanford and in our lab at JILA. For comparison, you might wonder about, for instance, non-classical light, like squeezed light. Where's that sitting on this plot? So for instance, the most recent results I know of are sitting here at sort of, around 15, 16 dB. So we can generate this entanglement now, but it's really interesting to ask, can we start applying this in quantum sensors? And so what has been operated with a phase resolution at the output of the sensor with a phase resolution below the standard quantum limit, and that's been done for clocks in several groups, in magnetometers, but actually has not been done in Matterwave interferometers. And so we were interested in really pursuing, since this is such an important technology. So this work is actually was done by 2 graduate students in the lab, Cheng Yi and Graham Grev. And this is on the archive. If you want to look it up, it will appear in Nature in just a little bit. So if you haven't gone to a lot of ICAPs yet, if you're young, you may not know what a Matterwave interferometer is. Let me just remind you what a Matterwave interferometer is. The idea is that you have atoms, and they have some center of mass wave packet describing them in quantum mechanics, and you can use pulses of light to impart recoils to those atoms, and even put them in superpositions of having absorbed a photon or not. And as a result, they can actually recoil and move along different paths through space, and then you can use light pulses to recombine them and interfere those matter waves with each other, and you can actually sense things with that. So for instance, these are very, very powerful sensors for navigation, gyroscopes, accelerometers, gravimetry, measuring the fine structure constant, tests of QED, test atomic charge neutrality, searches for dark matter, dark energy, geodesy, exploration for resources, tests associated with gravity, looking for gravity waves, okay? There are all kinds of applications for these sensors. It's a very, very important class of atomic sensors, very powerful for exploring our universe. But so far, we haven't been able to take this concept of entanglement and introduce it into this type of sensor. So there were two proposals based on using QED approaches here, and a one-axis twisting approach based on just interacting with just the momentum degrees of freedom, which is related to what we're doing but different. Also recently, there were a method in Karsten Klim's group where they were able to use collisional interactions, like were mentioned in the previous talk. This was mentioned. Collisional interactions to entangle the atoms, then map between a spin degree of freedom onto momentum states. But in that system, they actually did not run a Matterwave interferometer. Okay, so I also want to clarify one more thing, that we're going to try and generate this Matterwave interferometer along the axis of a cavity that's vertically oriented. But it's really, I want to emphasize that we're creating a squeeze state, not of some bosonic-like mode. Like for instance, if I have a single ion in a trap and I do parametric driving of that system, I can create sort of a squeeze state. This is actually entanglement between different atoms in the ensemble. And so for instance, each atom will be in a superposition of two different wave packets, but each atom will also be entangled with an atom here and an atom here and an atom over there, okay? So it's entanglement between atoms. That's going to be the resource we're trying to generate. The cavity we're using has a free spectral range of about 6.8 gigahertz, a single particle cooperativity of about 0.5, a finesse of 130,000, a length of 2.2 centimeters, a mode waste of about 72 microns, a line width of about 51 kilohertz. We're doing this in rubidium-87. We typically use about 1,000 atoms. The collective cooperativity parameter is about 500, and that's the key parameter in these types of experiments. You want that much larger than 1. The temperature of the radial motion is about 1 microkelvin, and when we include some transverse confinement, that gives us a thermal radius of about 3 microns, much less than the waste of the cavity mode. So the atoms are tightly confined on axis. I also mentioned a number of years ago there was some work demonstrating a Matterwave interferometer in an optical cavity, but the finesse was much lower and the mode waste was much higher and much larger. And so as a result, it would be very difficult to do the kinds of experiments I'm describing today in that kind of system. Okay, so the idea is that we would like to let the atoms fall under gravity, but if we just let them fall with no confinement, they would actually very quickly, due to their finite temperature, move out of the cavity mode. So we provide a transverse guiding mode. It's a blue potential at 760 nanometers. We inject inside the cavity into an HG01 and HG10 mode that repels the atoms looking down the cavity axis here, so the atoms would stay on axis and interact with the cavity mode. We need to be able to provide momentum kicks by absorbing or emitting photons. And so the way we do that is we drive 2 photon Raman transitions between ground hyperfine states here. The hyperfine splitting in rubidium is 6.8 gigahertz, and we're actually driving on the clock states, so 10 to 20. There's a 2 photon detuning for this process. How do we get that light in the cavity that's detuned 80 gigahertz from resonance, so we can drive this 2 photon process? We drive 2 other longitudinal modes of the cavity, and we had to carefully set the cavity length so that those modes would be close enough to resonance that if we can send some light out, we can get enough light in the cavity to drive the 2 photon Raman transition, but not so close that we'd get very strong FM to AM conversion associated with laser and cavity frequency noise that can screw up your single particle rotations. So we can actually scan this 2 photon detuning, and we can actually ask how many atoms flip their spin when we apply it for a given 2 photon detuning. This allows us to map out the velocity spectrum as the atoms are falling along the cavity. So for instance, if we let them fall for about 15 milliseconds, we see this distribution. If we only let them fall for a shorter time, we see this distribution. So they're falling under gravity, going to larger 2 photon detunings. We can use this same mechanism to actually velocity select a group of atoms, so we can work with a very, very narrow momentum class of atoms. And so when we're done, that's actually the data. That's the spectrum, the red dash there. That's 800 atoms with an RMS spread of about 0.1 h bar k. So in order to make this work, and in fact, it's one of the true sources of power for Matterwave interferometry is the fact that you can provide quantized momentum kicks. So we'd like to see that we can do that. So for instance, we can prepare all the atoms and spin down, and at zero momentum is in a co-falling frame with the atoms. By zero, in fact, they're falling quite rapidly. But I'll call that zero momentum. Then we apply a pi/2 pulse with the Raman beams to split the wave packet, and then we apply a pi pulse to move this portion down to spin down, and then we look at a velocity spectrum. So we see two peaks are separated by 4 h bar k, like you would expect. We can also draw Bragg transition. So for instance, here where we don't change the momentum state, it's a 2-photon process. We apply a pi/2 pulse, and then we can apply subsequent pi pulses to this part of the wave packet to drive it to higher and higher momentum states. And here at the end, for instance, we've separated 0 and 10 h bar k in this system. So we can do all these operations that you would like to do with Matterwave interferometers, but inside of this high-finesse cavity now. So we can put this together to form a Matterwave interferometer. We apply a pi/2 pulse. The wave packets separate. We apply a pi pulse to flip their momentum states that allows them to re-overlap in space. And then we can interfere them with a pi/2 pulse and ask how many atoms come out in a given state. We can vary the phase of that final pi/2 pulse, and we can ramp it, and we see a Matterwave interferometer fringe. Here, this contrast is pretty high, but when we typically have optimized things, we get about 90% contrast on these fringes. We can also see that there are actual, Matterwave packets involved. If we imbalance the time T2 minus T1 in this interferometer, we could try to interfere either too early or too late, and then we see that the contrasting interferometer goes down. So this really allows us to see that our RMS momentum spread is about 0.07 h bar k, and if it were a minimum uncertainty state, that would correspond to a delta X of about 900 microns. Sorry, 900 nanometers. Is it an inertial sensor? Yes. You predict that if you build such an interferometer and you let it fall under gravity, that you should see a phase shift of this fringe that scales like t squared, and that's exactly what we see over here. The dots have very, very small error bars on them. We're unwrapping all those 2 pi's. Okay, so we've got our Matterwave interferometer. Now, what about the idea of introducing entanglement? So for entanglement, here's the fundamental mechanism. The idea is that there is a state-dependent shift of the cavity resonance frequency. And so we take a mode of the optical cavity and we tune it close to resonance with the up to E transition here. It's detuned by maybe about 200 megahertz. And what that means is if we put atoms in this spin-up state, here's the cavity resonance frequency. When we put atoms in that spin-up state, it will actually shift in frequency. So you can describe that kind of interaction as a QED Hamiltonian, where you have a QED interaction between the cavity and the atoms that couples the population measurement projection operator N up to C dagger C over here. This leads to this cavity frequency shift. Okay, that sounds very quantum mechanical, but I really want to just step back and say, look, at the end of the day, it's very classical physics. Every atom in spin up looks like a little piece of glass that has some index of refraction associated with it. And so if you put glass inside of your optical cavity, you change the round trip optical path length, and that shifts the cavity resonance frequency, okay? But what's really magic here and makes this sort of interesting for quantum mechanics is the fact that measuring the shift of the cavity resonance frequency helps us to infer how many atoms are in spin up, but does not reveal which atoms are in spin up. So if each atom is in a superposition of these 2 states, by measuring this cavity frequency shift, we can make a measurement of N up, but not which atoms are in N up, and that's what makes it special. Here's an example of such a QED measurement where we send some light at the cavity and we look at the reflected light from the cavity in homodyne, and you see a dispersive shift as the probe crosses the cavity resonance frequency. And then if we put atoms in the cavity, we see this dispersive shifts, and we really want to measure how big that shift is to infer N up. If we then apply a pi pulse, a Raman pi pulse, we can measure the number of atoms that were in spin down, and that allows us to have an effective QED Hamiltonian for measuring the spin projection JZ. Okay. So if we can make that measurement precise enough, it says that even though we started with some very large quantum uncertainty in the, say, the polar angle associated with this collective block vector describing the system, if the measurement resolution is below that original uncertainty, we will localize the quantum state to a smaller angular region on the block sphere. So for instance, on one trial, our measurement outcome may tell us we're at the equator, and we'll know that it's actually constrained to be closer to the equator than the original coherent spin state. And then on the next trial, we may find that it's a bit above the equator, but again, the angular uncertainty and where we know it's pointing on this trial is improved. And so even though it's probabilistic in terms of what measurement outcome you will get, it's deterministic in the sense that both of these states are completely usable to run a Ramsey interferometer with, or some kind of Matterwave interferometer. So if we optimize the measurement by basically varying how many photons we send at the cavity in order to measure this cavity frequency shift, we see that we get an optimum here below the standard quantum limit, and that's about 3.4 dB directly observed, squeezing below the standard quantum limit, but with momentum states involved, which is what we wanted, okay? I want to emphasize that the numbers I'm going to report are the directly observed numbers with no background subtractions or corrections or anything else. It's what we see out of the experiment. There's another way we can introduce entanglement, and that's actually by introducing an effective spin-spin interaction. And this approach really follows what was worked out by Ian and Monica and Vladen back in 2010. And the basic idea is, let's again begin with the fact that the cavity resonance frequency depends on JZ. So if I apply a pump to this cavity, because from trial to trial, that cavity mode will shift depending on the value of JZ, the amount of light that will get into the cavity also depends on JZ. And so what that means is I can take my Q&D Hamiltonian, I can replace C dagger C, the number of photons inside the cavity, with JZ, and I end up with a Hamiltonian that looks like JZ squared. And why is that interesting? It's interesting because it allows you to create a shearing of your original quantum noise distribution. So if you're above the equator, the quantum noise shears this way. Below the equator, it shears this way. If you apply it for some amount of time, you will find that there's an axis of this sheared noise that has reduced uncertainty relative to the original standard quantum limit. So a rotation through a small angle alpha will allow you to orient that wherever you want to use it as a resource. So here's an example of that where we apply this shearing operation, this one-axis twisting, and then we rotate the angle and look at the angular resolution versus the rotation angle alpha. And at about 100 milliradians, we see that we're below the standard quantum limit with about 2.5 dB of directly observed squeezing, again with momentum states involved. Okay, so we've got two different ways, one based on measurement and one based on unitary dynamics in order to create these squeeze states. But now let's see if we can actually, well, actually, let me make this one comment. The black points are actually the original unsqueezed Matterwave interferometer. But I want to be careful and say that really what this line represents is that this is the distance I'm below that line is the degree to which I can actually certify this is the improvement that arises from entanglement between the atoms, okay? It's not just a question of, is my interferometer better? It's a question of what fraction of it can I actually say arises from entanglement? Okay, so let's put this together to try and run an interferometer. Actually, we've been running a mini interferometer this whole time while we're generating the entanglement. We apply these entangling operations here and here, and then we end up with this entangled state, and now what we do is we apply a pi/2 pulse. So I've got this entangled state, and now I apply a pi/2 pulse that orients the state like so. It accrues some phase during the interferometer phi, and then that gets converted by the final pi/2 pulse sitting over here back into a phase deflection in theta, in the polar angle. And now you notice that actually the noise is reduced along the final measurement basis. So you actually get a reduction in the noise. So that's what we're going to try and do. So we set that up, and essentially what we do is we do one-axis twisting and then play around with that small rotation angle alpha that we use before we do this pi/2 pulse. And again, here are the red points at the output of the interferometer. We see that we're below the standard quantum limit. Okay, so this is something with a phase resolution below the standard quantum limit at the output of the interferometer. It's about 1.7 dB. We actually see that there's technical noise inside this interferometer that essentially from shot to shot that phase phi fluctuates. And so that means that after a few hundred microseconds, we actually lose our improvement over the standard quantum limit. But we think that that's actually arising from the spin labels associated with this interferometer. The fact that momentum and spin are correlated with each other for these systems. And so we think that if we can combine microwave and Raman and Bragg pulses, we'd be able to get rid of that spin label and do even better. Differential interferometers would allow us to get some common mode cancellation of noise. And also, it'd be really nice to squeeze using an optical cycling transition where the fundamental scaling of how much squeezing you can get scales in this experiment like square root of NC. It would actually roll over to NC. And in the past, that was one of our biggest leaps in our ability to create entanglement, was moving to this cycling transition. Okay. So I'm going to, now in the last little bit that I have here, I'm going to switch gears. And I'm going to tell you a little bit about some physics we've been doing in our strontium system, where we've been looking at sort of dynamics of many-body systems. And in particular, it really relates exactly to what Monica was talking about earlier. It's kind of some games we're playing with spin exchange. Okay, so what we're going to do spin exchange on is actually the millihertz transition line width in strontium. It's this clock state here, triplet P0. So that's a little m, not a capital M. It has a radiative lifetime of 118 seconds, plus or minus 3. That asterisk is so that I remember to point to this and tell you that 3 is because we measured it, and we did it using a double QED technique that allows us to extract the radiative lifetime in our cavity system. But we actually were looking at, in 2018, a spin exchange interaction where essentially it may take a while for this atom to decay to the ground state, but this atom over here could absorb it and go to the excited state. It's the same spin exchange interaction. So, but you can write this in terms of collective operators with some coupling constant out front, J plus, J minus. Where are the dynamical consequences that you could observe as an experimentalist of this spin exchange? You can rewrite J plus, J minus as total J squared minus JZ squared plus a single particle term I'm going to ignore, okay, a JZ term. Okay. And so if you look at that, that means that actually this JZ squared term, we've already actually heard about it. It can actually create entanglement for you. And this J squared term actually means that there's an energy cost associated with changing the length of your block vector, as might happen if you had single particle dephasing. So you might be able to protect yourself against single particle dephasing. So we actually applied this kind of spin exchange, but then we, in subsequent work, we moved to a 7.5 kilohertz transition so that actually the spin exchange interaction was just faster. So the energy scale was larger, the frequency scale was larger. And we were able to explore this kind of Hamiltonian and look at quench dynamics when suddenly you turn on a transverse field to rotate the system. And for instance, we could explore this phase diagram along this cut here and see this kind of phase transition, where you go from a region where spin exchange dominates to the single particle rotation dominates. And I'll just point to, there's actually a very similar experiment, but with short range interactions instead of all-to-all in Chris Monroe's group in ion traps in 2017. They explored something similar, but here this is being done with close to 1 million atoms. So we've seen this JZ squared, and we've had some fun with sort of looking at these dynamical phase transitions. We were also interested in asking, yeah, but can we really see this J squared, this gap protection? And in fact, I'll point out that this has been seen, this kind of gap protection has been seen in various systems, but actually right here in Toronto at Joseph's group, they were able to see a similar sort of gap protection in a degenerate Fermi gas. So here, at t equals 0, we start with all the atoms in the ground state, and then we apply a very fast pi/2 pulse to put the atoms in a superposition of the ground and optically excited state. And then we can actually look at the coherence, or the length of the block vector. That's what this plot is on the vertical, essentially. Length of the block vector versus time, in about a microsecond, the system just quickly dephases, and you lose your coherence. And that's because single particle dephasing is dominant at that point. At this point, the number of atoms we had said that, you know, sort of chi here, chi n is of order 0.4 megahertz. That's the size of the gap. So we can actually start increasing our atom number, and what we see is as we increase our atom number, actually now the coherence lasts for longer and longer and longer in this system. And it's a very rapid change in the sense that you see a dramatic change just going from 0.4 megahertz to 0.7 megahertz as chi n becomes larger than the, you know, energy scale or frequency scale associated with the single particle dephasing. Okay, the final thing I'm going to do is I'm going to loop back to the Matterwave interferometer. So I've told you about spin exchange, and now let's come back to the Matterwave interferometer with rubidium here, okay? And in, what I'm going to tell you is that we think we're seeing the first signs of not spin exchange, but momentum exchange inside of a Bragg interferometer in this system. And so in 2019, Athreya Shankar and Salvi and Chiafalo and Poli and Murray Holland proposed that, you know, if you had a ring cavity, perhaps you could use Raman lasers to dress momentum states and induce a spin exchange-like interaction in the system. And so we thought that we could probably pull this off in our standing wave cavity, so we gave it a shot. And so the basic idea is that you actually have a system where you apply a pump, but now it's much further detuned than before from the cavity. And if you imagine an atom in momentum state P naught, it could absorb that pump photon and emit a photon into the cavity. Okay? And where that photon would land might be resonant or not resonant with the cavity. So we can tune that by tuning the pump frequency. But now if an atom was in P naught plus 2h bar k, it could actually absorb that photon and flip over to P naught. So basically you could get an exchange of atoms flipping between momentum states mediated by the cavity, and you get a collective enhancement in that effect. So it becomes much larger than other single particle terms that you could imagine are there. So we set about to do that. So we're saying, look, we think there's going to be a J plus, J minus like spin exchange, except it's momentum exchange, no spin degrees of freedom involved. Let's look for this JZ squared like interaction. So we actually apply this pump for about 100 microseconds after the splitting pulse. We have to apply it right after the splitting pulse because, as I showed you earlier, the wave packets actually move apart from each other. And this only works when the wave packets are actually overlapped with each other, that you'll get strong spin exchange. So we apply it for about 100 microseconds while the wave packets are still overlapped. And then we can prepare a system where we prepare a block vector of these two states. So we're describing it as a pseudo-spin state above the equator, and that's the blue. And then we scan the pump frequency, and when the pump is about 420 kilohertz detuned from the cavity resonance, we see a resonance corresponding to a phase shift that accrues due to this applied spin exchange interaction. Now, you might imagine there are other things that could do this, so we do the experiment where, in fact, we do the red. We prepare a superposition below the equator, where actually you expect that the sign of the phase shift should flip if it's this JZ squared, and that's, in fact, what we see. So the data could be better, but actually this is data like Wednesday. We just saw this hot off the press. So we're excited about this. We think there's lots to do. We're interested in this gap protection. What would be the equivalent of gap protection here? It's actually interesting because it kind of says that if you could engineer a gap in these momentum states, a physical interpretation of it is normally you think of it as the atoms absorb a photon, a superposition of absorbing and not absorbing a photon, and so you get this recoiling wave packet. But if you have this gap protection on, it actually says they kind of would get glued together, and they'd recoil together, the two wave packets, and they wouldn't move apart from each other. And yet, there would probably still be an interferometric signal. That's what we think. So there could be some fun games to play if we could see that. We think that by adding additional tones, say on the other side of the cavity, we could drive the kind of pair production processes just like Monica was talking about earlier. Can we control this well enough to see one-axis twisting induced entanglement between the atoms? That's an open question. But we also have some ideas that with two tones and actually making a homodyne measurement of the light coming out of the cavity, we could do a direct QED measurement of the superposition phase. And what do I mean by that? I mean that we could essentially perform a QED measurement of the light leaking out of the cavity during this period. It would actually tell us the relative phase of the wave packet in this arm and the wave packet in this arm at the start of the interferometer. And then we can make a second QED measurement of that style just before the re-overlap or even at the overlap time. And we would never map onto populations as a way of reading this out, and perhaps we could do this below the standard quantum limit. So we think there are lots of really exciting possibilities for playing with this. So I didn't do the work. Really fantastic grad students and postdocs who do this work, as well as collaborators. So thank you to all of them. And we do have postdoc positions available, so talk to me if you're interested. Thank you.
Okay, so once again, we got the runners going up the aisles. Are there any questions before I go to Bill? Any online questions? No, so Bill, take it away. Here's the micro.
Right. Okay, so now you got this 1.7 dB in the interferometer by combining all that, and that's fantastic. But of course, we know the history of squeezing in anything, interferometers in particular, always waits until you can't get that gain by just upping the flux. So where are you relative to that? Do you have limits that say, oh, I can't use more atoms?
I don't. Really, we're doing this as exploratory physics to understand. Sometimes you tell yourself, well, of course you will be able to create an entangled Matterwave interferometer and run it below, but until you do it,
well, sure.
you don't know, right? So basically, this is a little bit of a until you do it. we're very far from any kind of state-of-the-art interferometer. And let me make a comment about squeezing. I think you're absolutely right. Any form of entanglement for quantum sensing has exactly that question. When do you use it? So let me use an example. Squeeze light is now being used in LIGO. Do you have to use squeeze light? Absolutely not. Just give me another $1 billion. Right? No, seriously, like another $1 billion, we'll just build a second LIGO and we'll get our 3dB, right? So I think that one thing you have to keep in mind when you're talking about entanglement in quantum sensors is that until you define what the classical constraint on the system is, it's unclear whether or not entanglement should be used in a given situation. And so I think you have to be very careful to define what are the classical constraints to decide whether or not it's the right approach.
Yeah.
Okay.
Good.
Thank you. There's a question over there, Brenda.
Yeah, hi. Yeah, thanks for the great talk. Just a question about the phase noise that you have in there. You mentioned that it was shot-to-shot variations from the phase encoding?
Yeah, so it's the fact that we see that the phase noise as a function of evolution time rises here. So we basically run the exact same sequence, but we replace all of the Raman pulses with the equivalent microwave pulses, and we see the same noise level. So we think that somehow we've got some noise process that's coupling to the spin degree freedom, which is why we think we might be able to make it better if we can develop techniques to map out of the spin degree of freedom into just pure momentum states. The blue points, which I didn't pause to explain, are saying that, well, look, what if I just don't apply that pi/2 pulse so that inside the interferometer, actually the squeeze quadrature remains along Z, okay? And then I don't apply this final pi/2 pulse either. I just, I apply the pi pulse in the middle to re-overlap, but I just sort of always leave the squeeze quadrature along Z. Then in fact, you see that, it stays quiet out to longer time. So it's definitely noise in phi that sits inside the interferometer that's masking it. Did that answer the question?
Yes, and I was wondering if it's gonna, make it worse once you increase T even more, accounting for vibration noise and such.
Yeah. Look, basically, every problem you have in a real Matterwave interferometer appears here. And so what we have done is we've tried to hit a sweet spot that's a compromise between realizing a Matterwave interferometer and also having a system where we could see entanglement in it. So of course, if you want to scale this, now you've got to get serious about being a precision measurement person and handling all that noise. But we do think that there are techniques, for instance, various sources of noise that you can get common mode. So for instance, there's always kind of noise in your local oscillator associated with any kind of quantum sensor, and often you end up making differential measurements as a way of dropping out that noise and looking at some differential signals such as in gravity gradiometers, this kind of thing.
Last question.
James, beautiful results. Congratulations. I'm curious, this confining beam, does that affect in the end the interferometer use? Is this just something you're using for now, and later we have to do it with trapped atoms, or how do you see the future of squeezed atom interferometry?
Yeah, so I think that the question is, what about this this guiding potential? I think anything that a guiding potential that you can dream of that would do a bad thing to your interferometer will do the same thing here. You say that the atoms don't see any light from the blue potential, but in fact they're at finite temperature, so they go off axis. And because we have this mode waste that actually has a finite Rayleigh range of a few centimeters, it means actually there's an intensity gradient, which actually leads to a systematic error, for instance, in your ability to measure an acceleration. But you could imagine if people could figure out how to do these light guides, where people have gotten very long coherence times, where they do these painted potentials, right? And they want to build rotation sensors, that you could imagine a system where you build some painted potential that sort of overlaps with your cavity mode, but then the atoms can leave it, right? So I can't tell you exactly what the roadmap would be for building a 100-meter scale Matterwave interferometer with entanglement on it. But I can at least see some plausible applications where you could have some guided Matterwave interferometry that might be useful.
Thank you.
We actually have an online question from Ben Stool. Can you give a quick explanation of why you still expect to see an interferometer signal if the momentum exchange operation is performed over the entire time of flight?
Yeah. Yeah. Sorry, I want to, if I can get to it. Okay, so it kind of goes back to this question of, would there be an interferometer signal? I think that there would be, and the reason I think there would be, even if you imagine that in some sense like the wave packets become glued to each other, because if you allow the atoms to fall, they're falling with respect to your optical phase reference, right? And so as a result, when you apply your final pi/2 pulse, the local phase of your phase reference will have changed. And as a result, you'll essentially be reading out how many ticks of my ruler have I fallen down. So I think that there will still be a signal involved there.
Sounds good to me. Hopefully
That's what I think.
satisfies Ben.
Yeah.
Great. So I think we're on to our coffee break. Thank you very much to both speakers, Monica and James. So we're back at 3:40.